Picture this. You're standing at the bottom of a staircase with 45 steps. You can hop up one step at a time, or two. Simple question. How many different ways are there to reach the top? Take a guess. 10, 100, 1,000. The real answer is 1,836,000,000 ways. From a 45-step staircase. And here's the twist that makes this the most asked warm-up in coding interviews. If you try to count those ways the obvious way, your program would run for longer than you will be alive. But the fix is 4 lines of code that finish instantly. Over the next few minutes, I'll take you from that brute force disaster all the way to the optimal solution. The way a senior engineer would walk an interviewer through it, out loud, step by step. And I promise by the end, you'll see the sequence hiding inside these stairs that's been famous for 800 years. Let's nail the problem down, because a good interview starts by making the question precise. You've got a staircase with n steps. Each move, you climb either 1 step or 2. We want the total number of distinct ways to get from the ground to the top. Let's do the tiny cases by hand, because they will drive everything. 1 step, there's exactly 1 way, a single hop. 2 steps, 2 ways, 1 plus 1, or a single 2. 3 steps. Now it gets interesting. 1, 1, 1, 1 then 2, or 2 then 1, that's 3 ways. Notice that 2 then 1 and 1 then 2 count as different, because the order you take the steps matters. So far the counts are 1, 2, 3. Keep those 3 numbers in your back pocket, because we're about to discover they're the start of something you will absolutely recognize. So, how do we count for any n? Here's the key question a strong candidate asks. What was the very last move? To land on step n, your final hop came from exactly one of 2 places. Either you were on step n-1 and took a single step, or you were on step n-2 and took a double. There is no other way to arrive. So, the number of ways to reach step n is simply the ways to reach n-1, plus the ways to reach n-2. That's our recurrence. Ways of n equals ways of n-1 plus ways of n-2. The base cases anchor it. 1 way to stand at the bottom and 1 way to reach the first step. Translate that straight into a recursive function, and you've got a working solution in about 4 lines. It is correct, it is elegant, and, as we're about to see, it is a performance catastrophe. Let's watch it blow up. To compute ways of 5, we need ways of 4 and ways of 3. But ways of 4 also needs ways of 3, so we compute ways of 3 twice. Go deeper, and it's worse. Ways of 2 gets computed 5 times, ways of 1 even more. The recursion tree branches in 2 at every level, and it recomputes the same answers over and over, like someone recounting the same pile of coins every single time you ask. The number of calls roughly doubles with each step. That's O of 2 to the n, exponential time. For our 45-step staircase, that's over 1 billion calls. For step 50, tens of billions. Your laptop just sits there and grinds, while the interviewer quietly writes, doesn't recognize the redundancy. The logic is perfect. The waste is fatal. And spotting that waste is the entire game. Here's the realization that turns this from exponential to instant. Look at that giant tree, and you'll notice something. We are not solving 1 billion different problems. We're solving the same tiny handful of problems again and again. In computer science, that has a name: overlapping subproblems. And there's a second property. The answer to a big staircase is built cleanly out of the answers to smaller staircases. That's called optimal substructure. When a problem has both of those, overlapping subproblems and optimal substructure, It's a flashing neon sign that says dynamic programming. And dynamic programming is not some scary advanced topic. It is one idea, almost insultingly simple. Never solve the same subproblem twice. Remember your answers. Everything else, memoization, tabulation, all the jargon, is just two different ways of doing that one simple thing. Let's do the first one. The first way is called memoization, top-down. We keep the exact same recursive solution, the one that's easy to reason about, and we add just one thing, a memo, a little notebook. Before we compute ways of n, we check the notebook. Already solved it. Return the stored answer instantly. Haven't seen it? Compute it once, write it down, and never touch it again. That's the whole trick. Watch what it does to the tree. The first time we compute ways of 3, we store it, and every other branch that wanted ways of 3 now gets it for free, so entire subtrees just vanish. The billion calls collapse to about en calls, one per step. We went from exponential to linear time, O of n, purely by refusing to repeat ourselves. Top-down memoization is often the fastest to write in an interview because you barely change your original brute force code. You just bolt on the cache. The second way flips the direction. Bottom up, called tabulation. Instead of starting at the top and recursing down, we start at the bottom and build up, filling a table as we go. Make an array, dp, of size en plus 1. Set dp of 0 to 1 and dp of 1 to 1. Those are our base cases. Then just walk from 2 up to n, and at each position, apply the recurrence directly. dp of I equals dp of I minus 1 plus dp of I minus 2. Each entry is simply the sum of the two before it. When you reach dp of n, that's your answer. No recursion, no call stack, no notebook lookups, just a clean loop filling a row of numbers left to right. Same O of n time, and a lot of interviewers actually prefer it because there's no risk of a stack overflow on a giant staircase. And if you've been watching those numbers fill in, you might be getting a very familiar feeling. Hold that thought. Now the move that makes an interviewer nod. Look at that tabulation loop again. To compute the next value, how much of that big array do we actually use? Only the last two entries. Everything before them is dead weight, just sitting in memory. So throw the array away. Keep two variables, call them previous and current, slide them forward one step at a time, and at each step, the new current is the sum of the two. When the loop ends, current holds the answer. We just dropped the memory from O of n down to O of 1. Constant space, no matter how tall the staircase is. This is the textbook optimal solution. Linear time, constant space, about 4 lines. And going from an array to two variables is one of the single most common "can you do better on space" follow-ups in interviews. So bank that pattern, because it shows up absolutely everywhere. Now for the plot twist I promised. Go back to those numbers we kept computing. 1, 1, 2, 3, 5, 8, 13. Each one is the sum of the previous two. That is the Fibonacci sequence, the most famous sequence in mathematics, written down by Leonardo of Pisa more than 800 years ago, while he was modeling how fast rabbits breed. The number of ways to climb a staircase isn't merely like Fibonacci, it literally is Fibonacci, just shifted over by 1. And this sequence is hiding all over the real world. The spirals of seeds in a sunflower, the arrangement of leaves around a stem, the branching of trees, the spiral of a nautilus shell. They all follow Fibonacci because it's nature's most efficient way to pack things. So when an interviewer asks about climbing stairs, they're really checking one thing. Can you recognize a classic recurrence wearing a costume? The best candidates just say it out loud. Oh, this is Fibonacci. And that one sentence signals you see the pattern, not just the problem. Let's write the final solution and dry run it, because talking is cheap and a trace proves you're right. Here's the whole thing. If n is 1 or less, return 1. Set prev to 1 and cur to 1. Loop I from 2 through n. Compute next as prev plus cur, then slide. Prev becomes cur becomes next. At the very end, return cur. 4 real lines of logic. Now, the dry run, let's do n equals 5. We start with prev 1, cur 1. I equals 2, next is 1 plus 1, which is 2. Slide. So prev is 1, cur is 2. I equals 3. Next is 1 plus 2, 3. Now prev 2, cur 3. I equals 4. Next is 2 plus 3, 5. Prev 3, cur 5. I equals 5. Next is 3 plus 5, 8. Prev 5, cur 8. The loop ends. We return cur 8. 5 steps, 8 ways. Always dry run your recurrence on a small case exactly like this in an interview. It catches off by one bugs and it shows the interviewer you actually trust your own code. Let's talk about the traps, because this is where good candidates separate from great ones. Trap 1. The base cases. Get n equals 0 or n equals 1 wrong, and every value after it is wrong. So always sanity check the smallest inputs first. Trap 2. Off by 1 on the array size. Your DP array needs n plus 1 slots, not n, or you'll walk right off the end. Trap 3. Overflow. These numbers grow exponentially. The ways to climb 90 steps already blow past a 32-bit integer. So in a language like Java or C++, you reach for a 64-bit long. And crucially, you mention it before the interviewer has to. And the biggest conceptual trap of all, do not try to be clever and guess a closed-form formula, and do not get greedy. The safe senior move is always the same rhythm. State the recurrence, prove it on a tiny example, then optimize. Recurrence, memoize, tabulate, reduce space. Every single time. Here's what really makes this interview ready. Climbing stairs is the doorway to an entire family of problems, and interviewers love to walk you up the ladder. First rung. What if you can climb 1, 2, or 3 steps at a time? Same idea. You just sum the last 3 values instead of the last 2. That's the Fibonacci version. Next rung. What if you can take up to k steps? Now you sum the last k values, and a sharp candidate keeps it fast with a sliding window sum. Then, minimum cost climbing stairs, where each step charges you a toll, and you want the cheapest way up. Same recurrence, except you take a minimum instead of a sum. Then the frog jump, decode ways, unique paths on a grid. All of them share the exact same skeleton. Define the state, find the recurrence, handle the base cases, then optimize the space. Master this one problem deeply, and you've quietly learned the template for a dozen others. That is leverage. Let's bring it home. Climbing stairs asks how many ways to the top, taking 1 or 2 steps at a time. The last move came from 1 step down or 2 steps down. So ways of n equals ways of n minus 1 plus ways of n minus 2. Brute force recursion is exponential because it recomputes the same subproblems over and over. The instant you spot those overlapping subproblems, dynamic programming makes it linear. Memoize it top-down or tabulate it bottom-up. Then you notice you only ever need the last 2 values, and you drop to constant space. And the punchline, it was Fibonacci the whole time. State the recurrence, prove it small, optimize the space. That rhythm will carry you through half the dynamic programming problems you will ever see. If you want to practice this live, with an interviewer that pushes back with real follow-ups, come do it free at crackit.io.